Welcome to the Automotive Diagnostic Podcast. We're going to explore ways to sharpen our diagnostic skills, find learning resources, and hear from experts in the automotive field. Hello and welcome to another episode of the Automotive Diagnostic Podcast. My name is Sean Tipping. I'm the host of the Automotive Diagnostic Podcast. This is installment number 2 of our 3-part series on airflow measurement systems for automotive engine controllers. Last episode, if you haven't listened to it, part 1 was about mass airflow sensors, a little bit of detail and testing on those sensors. Today, part 2 is actually going to be solely dedicated to a method of testing that we can use to help us determine the accuracy of a mass airflow sensor. If you remember where we left off on the last episode, we talked about how the mass airflow sensor is kind of a wild card as far as inputs go to an engine computer. And unless you've worked on the same vehicle, the same engine, a number of times, you're going to be pretty hard pressed to know exactly what the incoming air mass should be at a given engine temperature and RPM. We just don't have a component we can bolt onto the air intake and measure that and compare it against the mass airflow to see if it's accurate. So we need something to help us out. Oh, and by the way, I should mention, I did have a listener tell me that he has a table that he has developed himself from known goods that references RPM versus grams per second, and he's going to share that with us. I'm actually just waiting to get that up on the Facebook page. So if you haven't checked out the Facebook page, please do. Just search Automotive Diagnostic Podcast on Facebook and ask to join. I will let you in right away. But let's talk about this method of testing. This is volumetric efficiency testing, or a VE test. And this actually has some other uses as well, but one of the things we can use it for is to check the accuracy of a mass airflow sensor. So let's talk a little bit about what the test is first, what we're talking about, and then we'll relate it to mass airflow sensors. So what is volumetric efficiency of an engine? This is a ratio of actual engine breathing volume to displacement. What I mean by that is, let's say we have a hypothetical 2-liter engine. Okay, so this would be the displacement of the engine. If you take all 4 cylinders, each cylinder divided up equally would be half a liter times 4, you've got a 2-liter engine. If that engine, during a 4-stroke cycle, meaning the engine rotated twice and every cylinder had its 4 events, everyone had an intake stroke, it ingested air on all 4 cylinders, and it took in and pushed out 2 liters of air on that 2-liter engine, that is 100%. Okay? If it was only able to move 1.5 liters of air through that engine, that would be a 75% volumetric efficiency. Okay, so we're just talking about how much air this engine can ingest, can take in and push out based on its size and compared to its size. Okay, if it only took in 1 liter of air during this 4-stroke cycle and it's a 2-liter engine, that would be a 50% volumetric efficiency. Okay, so when we talk about VE or volumetric efficiency, it's just how much air can this engine take in based on its size. That's really what we're looking at the most basic level. And again, we're talking about on the intake stroke, that piston comes down, creates an unpressurized space. The atmospheric pressure, or in the case of a turbocharged vehicle, the boosted pressure fills that cylinder with air pressure, and then we have our compression, power stroke, and exhaust is going to push that out. And really, the engine is just a big air pump. We're just moving air through it. And again, going back to the mass airflow, the computer needs to know how much air are we moving through that engine so that I can add the correct amount of fuel. But again, our VE test is going to actually help us measure how much air this engine is actually pushing through it, or at least how much air the computer thinks the engine is pushing through it. So the first question that we have to ask is, what numbers would we expect if we perform a volumetric efficiency test? Now I'm going to explain exactly how to do this. The how is pretty straightforward. It's pretty easy. But let's talk about numbers, because we're going to get a percentage when we're done. Again, I said if a 2-liter engine ingests 2 liters of air during a 4-stroke cycle, we call that 100%. Okay. But what numbers are actually expected on a real life vehicle? And that is kind of where there's some variables with this testing method, because engines have become much more volumetrically efficient with technology like variable valve timing and variable valve lift, variable intake runners, dual overhead cam engines. I mean, some of those have been around for a while, but if we compare them to engines of the early to late 90s, or going back even further than that, they are much more volumetrically efficient. They can move more air through that engine in a given amount of time, because here's the deal, there's not going to be, maybe I shouldn't say there's not, but you're going to find very few engines that can actually move 100% efficiency. There's always going to be some sort of parasitic drain, something that keeps the full volume of air from moving through that engine. And of course, we're talking about no restrictions. So the throttle's wide open at this point. And even at that point, with a wide open throttle, most engines cannot move 100% efficiency. That's just the fact of the matter. Now, some engines can do it better than others, but even a modern naturally aspirated engine, you may only see in the 80 to 90% range as a result from this test. And that's completely normal. That's everything functioning correctly. Heck, I've seen some older, high mileage pushrod engines that 75% is actually a pretty good number on those. There are going to be some motors that are pushing 100, but it really does depend on what you're working on. And that's where the variable on this test does come in, because we can't say for sure, unless you have a lot of known goods on a particular engine, we can't say for sure what's good. But I do like to use the range of somewhere between 75 to 90%. Now, if it's over 90%, great. That can also actually indicate an issue too, though. We'll get there. But that's just the basis of the numbers that I like to use. If it's below 75%, I know we have an issue somewhere, whether this engine can't breathe or there might be an issue with the mass airflow. Again, I'll explain how that ties in here. So really what we're doing with this test, again, is analyzing the ability of the engine to breathe by calculating its volumetric efficiency. So let me ask you this. If we got a low number from this test, let's say we got a 65 on a 2015 engine that had dual overhead cam and VVT. 65 is too low. That pretty much for any engine, if you see 65% as a result for your VE test, it's going to be low. What could cause that engine to not breathe properly? What could cause it to not ingest air or not being able to expel air during that 4-stroke process? So we could have all kinds of things, actually. We could have a restricted exhaust. We could have a restricted intake. Not as common, but it does happen. I've seen plastic bags get sucked up into air filters. I believe I saw a case study somewhere. It wasn't mine, but it was a case study somewhere of a squirrel getting lodged in an intake tube and choking out an engine. That's an intake restriction. Maybe the filter's plugged up with stuff. So it does happen, is my point there. So we could have an intake restriction, we could have an exhaust restriction, or we could have a mechanical engine problem. We could have a breathing issue that maybe the valves aren't opening at the right time. Okay, so we could have a camshaft timing problem that could cause a breathing issue with the engine. All of these are possibilities on why we might get a low number when we perform a VE test on a car. So you might be asking, well, how does this tie in with a mass airflow sensor? And we will get there, but I want to set up the test and explain the test before we go any further. If you get a low number on a VE test, it's just an indicator of a whole bunch of different breathing faults. It just means if this test fails and I get a 65, I have got a breathing problem with this engine. It is not ingesting enough air. But there is another possibility here, and the air measurement is going to be part of that as well. our mass airflow is going to play a role in this test. So to explain how the mass airflow ties in with this test, I am going to explain how we do this test and what's required to do this test. Now, the first thing on my list is going to kind of set this up as to why this pertains to mass airflows is you have to have a mass airflow sensor vehicle in order to do this test. And that's just how it is. You cannot perform a VE test, at least not the way I'm describing it here, without a mass airflow. Okay, so if you have a speed density vehicle that only uses a MAP sensor and not a MAF sensor, you're not going to be able to do this test. It's just not going to be possible because we use the mass airflow measurement in grams per second as an input for this test. And that is where the mass airflow can throw off this test, because imagine if our mass airflow is skewed in one direction or another and we're using this as an input for a test, it's going to throw off our numbers, isn't it? That's where this sensor can come into play. But let's talk about how this test is done. The second thing you're going to need is a VE calculator. Well, guess what? Those are free. You can find them online. There's a number of them out there. I'll tell you the one that I prefer, and I will put a link in the show notes as well. The ATG VE calculator, and just Google ATG VE calculator or click on the link in the show notes and you will be able to find it. I like this one because it allows you to put in atmospheric pressure as well. Not all VE calculators do, and I highly suggest you do that because when we get to turbocharged vehicles, you want to have that input. It's important for this test. The next thing you're going to need is a scan tool that displays the following PIDs. Mass airflow in grams per second, RPM, I think you can find that on any scan tool, and the intake air temperature. And I guess if you didn't have the intake air temperature, you could figure out what the temperature is outside, but I like to know what it is right at that mass airflow sensor, where it's being measured going into the engine. Now, here's the thing. Those are our three data PIDs: mass airflow, RPM, and our IAT, intake air temp. You can always, at least for every vehicle I've ever seen, you can always find these in global OBD2 data. So you don't even need a fancy scan tool in order to do this. Plug in, go into global, find these three data PIDs. That's what we're going to need to do this test. Oh, and one last thing, you do need to know what the actual barometric pressure is in your area, but just Google the weather for where you're at and you should be able to find that pretty easily. So how to actually do the test once we have all this set up? We've got our scanner connected and we have those three data PIDs up. We have our VE calculator ready, but we're not going to use that until we're there. We have a mass airflow sensor vehicle, obviously, and maybe we have some sort of concern about the engine breathing. You're going to graph those data PIDs, those three data PIDs I talked about, and then you're going to accelerate at wide open throttle to the highest RPM you're able to obtain before a shift point. So I like to do just like a first gear run so that I don't have to accelerate the vehicle to a high speed. Now, please do be safe while you're doing this. Be considerate of the customer's vehicle, where you are driving. The other thing I like to consider too is that, you know, if this vehicle has 200,000 miles on it in black oil, maybe I don't want to go out and perform this test. And I might even let the customer know what I'm doing so they don't think I'm just going out and rotting around in their vehicle. I'm doing a professional test here, but I do need to accelerate the engine to its highest RPM point before a shift point. That's part of this test. So again, be safe, and it's even better if you can have someone with you, because you don't want to be staring at the scan tool while you do this. You're going to hit record on the scan tool, set it off to the side, and you're going to focus on driving so that you don't crash the car, because again, you're accelerating wide open throttle. We don't want any throttle restrictions during this point, or it's going to throw off the test. We want maximum airflow through this engine. That's the whole point of this test, is to obtain max airflow through the engine and to measure it and see what it is. Does it compare to what it should be on this vehicle? Just some things to keep in mind. Once you've achieved the peak RPM, head back to the shop or a safe place where you can pull over and enter the numbers into the VE calculator. So if you pull up the calculator, the ATG calculator, it will have you enter the engine size. You can find that. It's going to say engine RPM. Now, if you go to your graph data, you want to find the peak RPM where it hit the highest point during engine operation, right before shift point, or right before red line. We want to find that highest RPM point. You're going to enter that as RPM, and at that same point, you're going to look and see what were the grams per second for the mass airflow. You're going to enter that into the next area. So that is our mass airflow measurement. It's being used in this calculator. It is comparing engine size and engine speed to the amount of air going through that engine at that point. And this calculator is able to figure out roughly what it should be and give it to you as a percentage. You're also going to enter the number of cylinders and the air intake temperature. And again, you're going to enter your barometric pressure because it matters how much pressure is pushing down on that car, how much atmosphere is pushing down on you. Are you in Denver or New Jersey? That makes a difference. So I do take the time to figure out what's the barometric pressure in my area, and it's always around the same. Weather affects it a small amount, but for the most part, it's the same. But I enter that in there. I put in the barometric, and then you just hit calculate, and it's going to punch out a number for you. It's really that easy, and this is free. You can download it onto your phone or just do it online, and it's going to give you a number. And that number will be in a percentage from 0 to 100. So we're looking for something that is above 75. If it's a newer vehicle, maybe I'd expect even closer to 90. But if I see below 75, I am concerned about the breathing of that vehicle. So what does it mean if the test passes? If I get 90% on this, what does it mean for it? Well, it means that my engine is breathing properly, and most likely my mass airflow sensor is reading correctly for that engine. At least at a high RPM range, that mass airflow sensor is reading correctly. And so I don't need to pursue things like timing and exhaust restriction and intake restrictions or unmetered air for the mass airflow, anything like that. But what if it fails? What do I do? This is where the VE test can be used to help us identify a mass airflow. You want to use this VE test in conjunction with your fuel trims and O2 sensor readings. Okay, so I'm going to give you 3 situations here. Well, the first 2 would be with a low VE number. Let's say we got 65 out of this VE test on this particular vehicle. So if the VE is low and the fuel trims are positive, meaning the fuel trims are in a positive correction, they are adding fuel to correct for a lean condition, I want to check for a mass airflow that's underreporting or maybe unmetered air, but let's focus in on that mass airflow. So we use the mass airflow as a portion of this calculation. Okay, we're putting that grams per second of air at the peak RPM into the calculator. So let's just make up a number here to make the math easy. If that engine was supposed to be drawing in 100 grams of air per second at that given RPM. That's 100% efficiency. And the mass airflow is skewed, and it's only showing 75 grams per second, even though the engine is actually ingesting 100. You're going to get a low VE number from that. Even though the engine mechanically is breathing the air, the mass airflow input can throw this number lower than you would expect it to be. And this is where we can pick out a mass airflow. But the other key to this is to look at your fuel trims, because if a mass airflow sensor is underreporting, if it's telling the computer you have 75 grams of air, but it actually has 100 grams of air going through it, you're not going to get the right amount of fuel matched to that oxygen, and you're going to have a lean condition. So the O2s will report that, the fuel trims will reflect that. And so fuel trims are really the key here to help you pick this out. Now, do keep in mind, unmetered air, that would be false air, can also cause a low VE number when the mass airflow sensor may not be at fault, but the mass airflow sensor might be dirty, it might be skewed. That's how we pick out a underreporting mass airflow sensor. Now, if the VE is low and the fuel trims are pretty close to normal, not really out of whack any one direction, this is when I'm checking for an actual breathing problem, like a catalytic converter or a restricted intake, because the mass airflow in that case is reporting the correct amount of air. Even though it's low, let's say it's 65, again, we're just using made up numbers to make the math easy. It said there were 65 grams of air per second entering that engine, and that's what's actually being added, even though it's supposed to be 100. Well, it would add the right amount of fuel, but that engine's still going to have low power because the amount of air going through it is not enough. So we don't get enough power out of that engine. Now, there's one more category here, and I've actually run into this a couple times. It's helped me to identify an over-reporting mass airflow. So mass airflows can under-report. They can report less air than is actually entering the engine, but they can also do the opposite. They can over-report to the PCM. They can tell the PCM that you have 120 grams of air moving through there per second, as opposed to the 100 that actually is. So the computer's going to add fuel for 120 grams when there's only 100, and then you get a rich condition. So if our fuel trims are in the negative direction, correcting for a rich condition by removing fuel, and you have an abnormally high VE test, because here's what you're going to get from that VE test. You're probably going to get over 100%. I remember the vehicle that I did this on. It was a Hyundai Santa Fe with a 3.3 liter engine running rich all the time, negative trims. I did the VE test and I got 116 on this naturally aspirated 175,000 mile Hyundai Santa Fe. I'm sorry, that's not happening. That was not a performance vehicle in any sense of the word. That's just not, that Hyundai was not at 115% efficient, volumetrically speaking. It wasn't. So I know that, so I know somebody's lying here. It was the mass airflow. He was over-reporting the amount of air, so the computer added too much fuel, and our fuel trims reflected that. So bringing fuel trims into the mix with our VE test will really help us to identify what path we want to go down. But hopefully you see how that can help you identify a mass airflow sensor that is not reporting the correct number. It's not 100% accurate, but it can definitely help you to identify one. A couple things about VE testing. There are some data PIDs that we can use in place of this, and the one that I have found to be the most reliable or the closest to mass airflow testing, and I believe I originally saw the comparison to a VE test in a Scanner Danner forum. Somebody there had mentioned that this data PID is very close, and I've used it and I have found that it is definitely true, is absolute load. The absolute load data PID is very close to the VE test that we just did without punching everything into a calculator. It is just a data PID, it's a percentage, and you use it just like this test. Save you a little bit of number crunching and graphing and putting stuff into a calculator. You can just look at one data PID, accelerate it, and see what you get to. There is a calculated load as well, which is similar, but I found, again, not to be as close to this VE test as the absolute load. Now, everything 2012 and newer that I have seen has this absolute data PID in the global data. So if it's a newer vehicle, this makes it a lot easier. And again, if it's got a mass airflow sensor, you need that. But check your global data and check for the absolute load data PID, and that can be a quicker way to do this. We'll use the number in the same way, but just keep in mind the computer is doing the calculation rather than you taking the numbers and putting them into a separate calculator. The one other thing, and I actually learned this from John Thornton at a Vision class, and I think Scott Schotten mentioned this in a class as well. If you have a turbocharged vehicle and you want to use a VE test, again, it needs a mass airflow sensor, but if you do a VE test with a turbocharged vehicle, you're going to get a number that is over 100% because you're squeezing that air tighter and packing those cylinders more densely than it would be with a naturally aspirated engine. We're moving more air through the engine, we get more power out of it. It's the whole point of a turbocharged engine, but you'll get VE test numbers that are higher than you would expect you could see 140%, 120%. So what's good on a turbocharged engine? I mean, if 140% was good, if that was our known good, then 105% might be bad, but 105 on another car is good. So where do we go with this? Again, this was the tip that was given to me. If you take your boost pressure, and you do need to add atmospheric pressure to this, so this would be an absolute pressure of your boosted intake manifold, and you put that into the area where it has you enter the barometric pressure. So really what you're doing, you're putting boost pressure into the barometric. Now, again, make sure this is an absolute measurement, not a gauge measurement. But we're going to put that boost pressure into that field, and then we're going to punch the calculator in again. It is telling the calculator exactly how much pressure is pushing air into the cylinders. And then it takes that into account, and it will give you a number that is 100% and down. So you can treat it like a normal engine at that point. And that can help you identify a breathing fault in a turbocharged engine. So that's the last point on VE testing. If you haven't used that before, make sure you do, because again, it's just another tool in our toolbox to help us with a sensor that isn't always so easy to verify if it's slightly skewed. That's the trickiest problem I have had with mass airflows, is when they are slightly skewed. So give a VE test a try. Let me know what you think. Check out the Facebook group. I will be working on part number 3 to this installment, which is going to be speed density systems. So there's some different strategies that we're going to take to speed density systems as well. But that's all I've got for you today. Thank you for listening.